Hi everybody, welcome to term 3. Yay, lucky us, getting close to the, what's that thing? External exams. My brain is dead today. I've also been talking non-stop for the past 5 days, so my voice is gone as well. I was going to do a recap of what we did last term, but I'm pretty sure everybody that's in this did last term as well. If you didn't, give me a bell and I've got an overview video that I've already done from a previous one. So this term is all about industrial chemistry, green chemistry, chemical synthesis, actually producing things. So industrial chemistry in the context of this unit is about maximizing. So you got the industrial chemistry, which is maximizing the yield, and then on the other side we have the green chemistry, which is how do we do both? How do we make it better for the environment and get more out of it? And companies can get more bang for their buck. So I've put together like an overview of a lot of stuff we're going to do. Give you a couple of the processes that you really need to get acquainted with. We will do a brief overview. Don't think this will take a huge amount of time. Probably like last time, I'll do a couple of bonus videos and some exam prep as well, just to make everything up to the hour. So, industrial chemistry. This is where we go from. Sorry, this is where we go from just learning about chemistry to actually learning how we apply it. Part of this unit is about organic chemistry, and then others we're going to go back into unit 1 and 2 as well to have a little explore. So we're looking at how do we produce the most amount of product given one set of conditions. How can we alter the conditions that a reaction is occurring in order to increase the yield? So the two processes you need to know for this unit is the Haber process. The Haber process, oh, here's Ross. Classic Ross being like, So we're looking at the Haber or Haber process and the contact process. So I want everyone to take 30 seconds and quickly Google or think what equilibrium means, or dynamic equilibrium. Think back to grade 11. Why did I do that again? So the world's chemical industry is gigantic. Two most widely produced products are ammonia, which is the basis for explosives, it's the basis for fertilizers, and a number of other pharmaceutical products. The contact process produces sulfuric acid. Sulfuric acid is used in just about every kind of chemical synthesis. All of the drugs you take, even the illicit drugs, usually attach to a hydrochloric acid molecule for easy passage through the digestive system. It's in your batteries. It's in your stomach. So there's a massive chemical plant in Moranbah called Dyno Nobel, and it produces products like ammonia, ammonium nitrate. There's a lot of people that live in Moranbah that are quite worried about that, because after what happened in Beirut, when all of that ammonium nitrate went kaboom. So sometimes you have to take the good with the bad, right? Fritz Haber, he won the Nobel Prize in chemistry, brought the world out of food poverty by providing a cheap and plentiful nitrogen source. But he also made chemical weapons for the Nazis. So, we just don't talk about that side of things. So plants, the main nutrient they need is nitrogen to produce amino acids and proteins. I can't remember the exact statistics, but the production of ammonia through this process, you're basically making ammonia out of thin air. And it's also used to make ammonium nitrate. If you saw the explosion in Beirut a few months ago, that was caused by a huge amount of ammonium nitrate. So ammonia, we remember ammonia from our organic chemistry. We have an amine group. So if we mix ammonia and a haloalkane, we will get an amine. But we're not really talking about organic chem in this particular Uncolor episode because I'm very important, TV celebrity. So I want everyone to write this down, and then when I do, we're going to analyze what it means. So take 20 seconds to write that down. Right, anyone want to have a guess at what the important things to note here are? No one? Surely everybody remembers equilibrium. What does delta H mean in regards to chemistry? Or if it has a change in heat of minus, is the reaction losing or gaining energy or heat? No one? Okay, well, let's go through it. I'll write up on the board. That's my beautiful talented education center teacher. We're very important now. Okay, so the Haber process, Haber process, I have no idea how to actually say it. You guys realize now I'm not an English teacher. So we have N2, it's a gas. What's this mean? What does an arrow backwards and forwards mean? So, reversible, or the reaction is in a state of dynamic equilibrium, or the reaction will eventually reach a state of dynamic equilibrium. So the reaction eventually will get to a point where it is occurring in the forward and reverse directions equally. And there will be a percentage of product and a percentage of reactants. If we're wanting to produce and make as much money as possible, we want to have a higher percentage of product. Makes sense, right? Oh man, my throat. So, higher percentage of the product is the aim. We have a change in heat of minus 92 kilojoules. So what does that mean? Just going to grab some cold water while you guys think about what delta H minus 92 kilojoules per mole gives us.
Yeah, means.
Let me give you a hint. We have exothermic and endothermic reactions. What's an endothermic reaction and what's an exothermic? Exo and endo. So exothermic loses heat to the surroundings, like when you're burning something. Endothermic gains heat from the surroundings. I want you to remember this. Exothermic loses heat. When a reaction happens in the forwards direction, it loses heat. When it happens in the reverse direction, it gains heat. That's very, very important to remember. Okay. Remember that. We want the reaction, when it reaches this equilibrium, to have a higher percentage of product. And we can manipulate the conditions to do that. I'll show you how to do that now. I can click the right button. Okay. So, look at the Haber process. It is a reversible reaction and it is exothermic because the change in heat is minus, meaning it's losing energy. So we can manipulate this reaction by altering the temperature, the pressure, and there is more to this, which we will go through, but I'm just giving you an intro into sort of the way to start thinking. Catalysts won't affect the equilibrium. They just mean you'll get to the equilibrium point faster. So who remembers Le Chatelier's principle? I don't know how to say it. Any ideas? Sorry. So we can adjust the equilibrium point by changing the conditions. We change the conditions in which the equilibrium, in which the reaction is occurring, and the system will try and reestablish a new equilibrium point. Okay, so when we're looking at pressure, we are looking for the side. So which side here has the most number of gas molecules? So we've got N2 plus 3H2. So on the left, we have 4 moles of gas. On the right-hand side, we only have 2. This is, I'm going to use the whiteboard here. It's much easier to explain, isn't it? Trusty whiteboard. So we have a reaction. It is at equilibrium. On the left-hand side, we have 4 moles of gas. Here we have 2 moles. Pressure and concentration of the gas are inverse. So if I increase the pressure, think of this reaction happening in a box, right? And I think I'll just do the Haber process for this because it's quite brain numbing. So our reaction is happening in this box. We increase the pressure. This reaction is going to want to bring that pressure down. So we have 4 moles over this side and 2 moles over this side. So what the reaction will do effectively is shift the equilibrium, or shift the equilibrium by producing more of the product because there's only 2 moles of gas. So by doing that, the pressure will come down and we will end up with more ammonia and less reactants. If we decrease the pressure, the system would counteract that by producing more gas molecules by sending it the other way. So if we tried to do this reaction with very low pressure, we wouldn't get that greater yield. If we want to increase the yield, we can increase the pressure, because by increasing the pressure, we're favoring the side that has the least number of gas molecules. If we have so remember this change in heat. 95 kilojoules per mole. It's not a flattering camera, I need to put my webcam. So this means every time the reaction goes forward, it loses heat. Every time it goes backwards, it absorbs heat. No pressure loss. But if I increase the temperature inside our reaction, which way is it going to send the reaction to reduce that heat? Any ideas? So if I increase the temperature inside our box where the reaction is happening, and every time the reaction goes backwards, It absorbs heat. Do you think that's what it's going to do? I'm just going to deliver this lecture style where I just talk. Okay, I'm just going to talk. No more questions. So if I increase the temperature, the reaction will try to absorb that heat by going backwards. So we'll end up with less product. So in a reaction like the Haber process, whatever you want to call it, we want to lower the temperature because the reaction will then go to the right-hand side. Because every time it does that, we lose 95 kilojoules. So we lose 190 kilojoules every time it does that. So it will bring the temperature back up. Right. So theoretically speaking, we can just drop the temperature and ramp up the pressure, right, as high as we can. The problem with doing this is pressure is very dangerous and it's expensive. Low temperature will drop the rate of reaction. Sorry. But if we drop the temperature too much, then our rate of reaction will become so slow. That by the time we reach the point where we want to, it's not commercially viable. So here, if we turn the pressure up to 1,000 atmospheres and the temperature down to 200 degrees, we can get almost 100% of the mixture at point of equilibrium to be our product, which is ammonia. But 1,000 atmospheres of pressure is very, very expensive. I think it's something like $1,000 a day for every atmosphere of pressure that you're using. It's obscenely expensive. Remember our catalysts, our enzymes, and our inorganic catalysts. Ross, what's an inorganic catalyst? No, no one's going to talk. Okay, fair enough. So we can increase the, by dropping the temperature, we are decreasing the rate of reaction. By then adding a catalyst, we're speeding that reaction back up. Important thing to note, catalysts do not change the equilibrium position, but they increase the rate of reaction. So this means it's produced faster. In the Haber process, we use magnetite, which is an iron oxide. Catalysts lower the energy required for the reaction to occur, so the reaction will occur faster. But we have to balance the conditions. So we can't just ramp up the pressure because it's expensive. We can't drop the temperature down to minus 250 because the rate of reaction will be too slow. So in industrial chemistry, everything has to be a balance of what we're doing. So 1 to 200 atmospheres of pressure. Temperature, still pretty hot, but not very. And magnetite as the catalyst. So there is, now we're not just talking about science here, we're talking about industry, we're talking about practicality, we're talking about safety, we're talking about cost effectiveness. So the idea is spend the least amount of money to get the most gains possible. We'll go more into detail with these processes and the other equilibrium conditions we can manipulate. But we also have sulfuric acid. 231 million tons are produced every year. One of the most commonly used industrial solvents that we have. So we have, in making sulfuric acid, we can represent it as that formula. But it's a three-step process, and the middle step is reversible, and we can manipulate the equilibrium. So step one is not reversible. Step two, I'll give you 30 seconds to write these down. Step two is a reversible reaction, so we can manipulate the equilibrium position. It is effectively exactly the same as the Haber process. There's more gas molecules on the left than there is on the right, and it's an exothermic reaction. This will probably only go for half an hour because I really don't have much of a voice left this week. I'll make up for the time. So step two is where we can improve the yield. So just like in the Haber process, we can increase the pressure and decrease the temperature. I have got presentations on both of these processes. They both should really command about half an hour each when we get real in depth with them. But this is just an overview and introduction into the type of thinking that's required for this unit, rather than just learning about organic chemistry. So temperature decrease, the rate of reaction also decreases. So again, you're balancing pressure, temperature, cost, practicality, safety, and yield. You could get 100% product yield at the end, but it would cost you so much to do that that it's not commercially viable. So the actual conditions for producing sulfuric acid, we have vanadium pentoxide as, and what you'll find is they're usually metal oxides are the catalyst for some reason. If we decrease the temperature, we will increase the rate of reaction. I mean, there's still pretty high temperatures, but some reactions you can run at 5,000 degrees. If we increase the pressure, same thing again. And if we increase the concentration of oxygen, we can also manipulate the equilibrium. There's about 6 or 7 different ways we can do this, and we'll go in more in depth in later weeks. Okay, when we're synthesizing the industrial chemicals, we have to balance the equilibrium conditions. We can't just go ramping up the temperature, so ramping up the pressure, dropping the temperature, because everything has to be balanced. Because if we start putting 1,000, 10,000 atmospheres, it's going to cost you millions of dollars, and it's not very safe. If something were to fail at those kind of pressures, you would get a massive explosion. All right, my voice is gone, so I might leave it there for today, and we'll go through the Haber and contact process in more detail next week, and I'll do a bonus upload. I don't have any voice left, sorry guys. I couldn't stop talking for about the last 10 days. I'll upload this one and send it out, and I'll send out the materials as well. And yeah, I'll do extra over the next few weeks, or even just a whole separate upload and recording to make up for the time I just can't speak anymore. So I will see you guys next week.